Element 11.1, Risk and Hazards of Electricity. In this sub-element, we will be discussing the risk and the hazards related to the usage of electricity at our workplaces, how these hazards can affect our workers at the workplace, and how we can apply different type of approaches to evaluate the risk arising from these hazards at the workplaces. We need to discuss the introduction of electricity. Electricity is the flow of electrons through a conductor. A commonly used conductor is copper wire. For electricity to flow, the conductor must be arranged with a power source to make a circuit. A very simple circuit is shown in the figure, is where a battery and a light bulb have been connected together using copper wire to form a loop. Electricity flows in one direction around the circuit from one terminal of the battery to the other. As it passes through the bulb, the filament in bulb resists the flow of electricity, heats up and emits light. If the wire is disconnected from the battery or bulb, the circuit is broken and flow stops and the bulb goes out. The basic parameters of an electrical system, such as in the circuit, are shown: voltage, current, resistance. Voltage is the measure of potential difference or electrical driving force that is forcing electricity through the conductor. Its unit is volt. Current is the measure of the rate of flow of electricity through a conductor, and its unit is ampere. Resistance is a measure of how much a component in the circuit resists the passage of electricity. Its unit is ohm. There are three parameters which are linked by a simple relationship called Ohm's law, which is voltage is equal to current multiplied by resistance. One other characteristic of electrical system is the nature of the current flow. In our basic circuit, the current flows in one direction only, from one terminal of the battery to the other. This is referred to as direct current and is usual for battery supplied electrical system. The main supply, however, in domestic houses and workplaces flows forwards and backwards through the circuit and is known as the alternating current. The rate at which alternating current switches backward and forward is called the frequency. Frequency is basically the number of cycles per second. Its unit is hertz. Moving forward towards the hazards and risk of electricity. The hazards and risk of electricity are electrical shock, burns, fire and explosions, arcing, secondary effects. Accidents involving electricity frequently include two or more of these hazards and risk at the same time. Each will be looked at in turn. Electric shock. Before moving forward, we're going to discuss the definition of live and dead. When a system is connected to an electrical power source, it is described as a live system. Once it has been disconnected from its power source and all stored power has been released, it can be described as dead system. Electric shock occurs when a person touches the live surface, a conductor at a different potential difference to neutral and earth, and an electric current passes through their body. The electric current uses the body as a conductor. The current will therefore have pathway through the body from the point of contact with the live surface where the current enters the body to another point of contact with the ground or earthly surface where the electrical current leaves the body. Put simply, the human body can be thought of as replacing the light bulb component in our simple circuit which we have described and discussed earlier. When a person receives an electrical shock, it can have a range of effects. The most important factor that determines what the effects will be is the amount of current that flows through the body. The following table indicates the range of effects that might be experienced at different current flows. For the current of 0.5 to 2 milliampere, the effect will be the threshold of sensation, and for 2 to 10 milliampere, there will be tingling sensations, muscle tremor, and painful sensation. And current ranging from 10 to 60 milliampere, the effect will be muscle contraction, inability to let go, and inability to breathe. For the current ranging from 60 milliampere and above, there will be effect of ventricular fibrillation, cardiac arrest, extreme muscle contractions, burns at contact points, and deep tissues. The important thing to note here is that the current is measured in milliampere. 1 milliampere is 1,000th of ampere. When a person receives an electrical shock, it can have a range of effects. The most important factor that determines what the factor will be is the amount of current that flows through the body. The following table indicates the range of effect that might be experienced at different current flows. The table illustrates that at very low current, less than 0.5 to 2 milliampere, no sensation is felt by the person receiving the shock. Between 2 and 10 milliampere, the current starts to flow through the body and stimulates muscle to contract. This can be felt, it can cause muscles to tremble and it may hurt. But the person receiving the shock is able to control their muscles and can let go of live object. The current between 10 and 60 milliampere, the current start to cause more severe muscle contraction and these may become so strong that the person cannot control their muscle and they grip onto the live object. When this occurs, the muscle of the rib cage and abdomen may contract so that the person cannot breathe, which means that they cannot call for help and they may asphyxiate. Alternatively, the shock may cause a massive contraction of big muscle groups so that the person is thrown violently off their feet, hopefully away from the live object. At current flows above 60 milliampere, there is the possibility of ventricular fibrillation where the heart is no longer beating in a synchronized rhythmic manner, but spasmodically. This usually leads to cardiac arrest. As the current increases above 80 milliampere, the possibility of ventricular fibrillation becomes greater. Muscle contraction can become so extreme that bones are broken. Burns will occur at the entry and exit point, and in the tissues that the current has passed through, death become more likely as the current increases. Moving forward towards the several factors which influence the severity of injury associated with receiving an electric shock. The first was in voltage. As Ohm law shows, there is simple relationship between voltage and current. The higher the voltage, the greater the shock current through the body. The second one is duration. The length of time that a person is exposed to the flow of electricity is critical. For example, a current flow of 60 milliampere for 30 milliseconds is unlikely to cause a severe injury, whereas the same current flows over a period of 2 seconds can induce ventricular fibrillation and prove fatal. The third one is current path. The route that the electricity takes as it follows through the body is also very crucial. If it runs through the chest, it is likely to affect the heart. And then it's come the resistance. As Ohm law shows, there is a simple inverse relationship between current and resistance. The higher the resistance, the lower the current. Most of the body's resistance to the passage of electricity is because of the skin. A person with dry skin has a high resistance, but if their skin is wet or damaged, this reduces dramatically. The resistance of the person will be influenced by various factors, such as contact surface area. The more skin that is in contact with the live surface, the lower the resistance, the greater the current flow, at more severe the injury. Environment. Any environmental factor that reduce resistance will cause an increase in current flow and therefore increase the severity of the shock. For example, wet surfaces, humid air, and metal surfaces. And then clothing and footwear, which is worn by the person, will similarly affect resistance and hence block or reduce current flow. And in the end, AC or DC. AC refers to alternating current and DC refers to direct current. AC is capable of causing more severe effects at lower shock current than equivalent DC shock. Coming forward towards the electrical burns, people receive burns in two different ways during electrical incidents: direct electrical burns and indirect electrical burns. Direct electrical burns occur when the current causes overheating as it passes through the skin and the internal tissues of bodies. There may be entry and exit skin burns, and these will be full skin thickness. The internal tissues burn can be very severe and may prove fatal. Indirect electrical burns do not occur as a result of the current passing through the body, but when an electrical accident causes something to overheat and explode. For example, dropping a spanner onto a high voltage cable will cause a short circuit which results into a flash of radiant heat and an explosion of molten metal. Moving forward towards electrical fires and explosions. Electricity can cause fire and explosion in several different ways, which are: electric component may be faulty and overheat as a result, leading to fire. The system may be overloaded as too much current passes through it, which causes it overheat and causing fire or explosion. Overheating during charging. Many portable or mobile devices can become hot during the charging process. This is particularly the case if the equipment is faulty or of poor quality. For example, counterfeit mobile phone batteries and chargers. Equipment may be misused. For example, it may be connected into the main supply by pushing bare wires into the socket rather than using the proper plug. Flammable atmosphere may be present, which electricity ignites. This can happen in two different sets of circumstances. The first one is using the wrong type of electrical equipment and brought them into an already known existing flammable atmosphere. The second circumstance is a flammable atmosphere is accidentally created in an area where it will not be accepted, for example, due to the spillage. Electric equipment may produce heat or spark as part of its normal operation. For example, a fan heater gets hot during its use. If it is properly positioned next to a full waste paper bin, it may start a fire. One common cause of overheating electrical equipment is poor internal connection. When two electrical components are joined together, the connection between them must be well made and secure. A poor connection causes an increased resistance, which in turn leads to overheating at the connection point. Poor connections can occur because the connection was not properly made when the equipment was being manufactured or installed, but they can also occur as a result of losing of parts over time. Fixed installations such as distribution boards can suffer this type of failure. Arcing. Arcing is where electricity jumps across an air gap. It occurs in a limited way inside some low voltage electrical equipment. For example, portable electrical drill. The dangers associated with arcing increase at higher voltage because the distance that electricity can arc through air is determined primarily by voltage. The higher the voltage, the greater the distance. High voltage power lines can arc across distances of 10 meters through the air. The main risks associated with arcing are electric shock as a result of being struck by the arc, direct burns as a result of being struck by the arc, indirect burn from the radiant heat given off by the arc and from the melting of any equipment struck. Damage to the eye as a result of the ultraviolet light that is emitted by the arc. Secondary effects. The secondary effects are any sort of injury that result indirectly from receiving an electrical shock. Common secondary effect injuries occur when people undergo violent muscle contraction during an electrical shock incident. They may be thrown across a room and receive cuts, bruises, and broken bones as a result. If they happen to be working at height of a ladder, then even a relatively minor shock can induce enough of a reaction to cause a fall. Moving forward towards the dangerous activities which involve the electricity risk. Fixed and portable electrical equipment. A wide variety of workplace equipment is operated by electricity, some being fixed system, hand wired directly into the distribution system, others being portable appliances. The same hazard apply to all of this, but the risk can be different, especially with portable appliances. Hardwired equipment need to be inspected and tested to ensure connection and system components remain secure and operational, particularly cables that may be exposed to pedestrian and vehicle traffic. However, it is less likely to undergo the rigors of being unplugged and moved around the workplace. Portable electrical equipment can be defined as equipment with a flex and plug that can be moved from one location to another for use. Whether it is actually moved is irrelevant. A photocopier may never be moved, but it has a flex and plug and is therefore portable. A high proportion of electrical shock accidents involve portable electric equipment. As an example of vulnerable portable electric equipment, consider a small concrete breaker on a construction site. It is subject to frequent heavy use in an outdoor environment, often handled and transported and used by a variety of workers who may not own the item and therefore have little interest in taking care of it. Moving forward towards the condition and practices that likely to lead to accidents related to fire. Use of unsuitable equipment, for example, the use of non-intrinsically safe equipment in a flammable atmosphere, use of equipment in wet, damp, or humid conditions, misuse of equipment, for example, sticking wires directly into a socket rather than using a plug. Physical abuse of equipment, for example, pulling the plug out by tugging at the flux, carrying the tool by the flex, allowing the flex to be pinched, trapped, or crushed. Repairs carried out by unauthorized personnel or carried out badly, for example, split flex taped up with insulating tape. Continued use of faulty defective equipment, chemical damage to the flex, for example by corrosive wet cement, and in the end lack of routine inspection, testing or maintenance. Moving forward towards the use of electrical equipment in wet environment. Because water decreases the resistance of objects and environment